Hi fellow nerds, and thank you for watching today. In this short video, I'll be demonstrating how to make soap the traditional way, that is, using a strong base and an oil. I'll be using coconut oil without any other oils as it makes a really good lather and a great cleansing soap. I'll also be adding menthol, which I find gives a really nice cooling sensation and helps to soothe any itch you might have. Oh, and of course, I'll be blending the science with the demonstration, so hopefully it's a nice learning experience with some practical use. Okay, so let's briefly go over the safety rules when working with a strong base and menthol. Sodium hydroxide is a strong base and must be handled with gloves, safety goggles, and a lab coat. When sodium hydroxide is added to water, it generates a lot of heat, also known as an exothermic reaction, which can cause some of the water to vaporize. Do not breathe directly above the sodium hydroxide water, especially while it is still hot, as this can easily irritate your lungs and also your eyes. Menthol crystals are actually quite beautiful, but menthol is also irritating to the eyes and respiratory system, especially when it's in its pure form. So do not breathe directly near the menthol. But once the soap has reacted for 24 hours or more, the sodium hydroxide has basically all reacted and the menthol is trapped in the solid soap, making the soap overall much milder. Now, if we were using a different type of oil or a different ratio of oil to water to base, it may take longer to get to this point where the soap is ready to use or where it's safe. So this is specifically for coconut oil with sodium hydroxide in the reaction. So okay, now that we've covered the necessary safety measures, let's start with a little science. Sodium hydroxide is found in things like drain cleaners, oven cleaners, and household bleach. It dissolves in water, making the water very alkaline. Now, sodium hydroxide is also technically a salt, separating into a positively charged sodium ion and a negatively charged hydroxide ion in water, and that generates heat upon separation. Now, lauric acid is a major fatty acid in coconut oil, and as you can see here, it's mostly carbons. Of course, you're going to have hydrogen here that are not visible, but mostly carbons, and then at the end you're going to have that's the acid component. That's why it's called a fatty acid, and this is the carboxylic acid. And we need that functional group in order for this lauric acid or any fatty acid to be amenable to making a soap. So when we add that lauric acid, it really doesn't want to blend with the water in this stage of this experiment, because all the carbons don't like water, so that oil will separate or form droplets that don't mix very well. As you can see here, represented by these yellow oil droplets. So when we start this demonstration, we're going to be at a state where basically this oil is not really mixing with the water, and that's not going to be very good for making soap. So we have to rely on this strong base in order to allow the oil to mingle with the water and to react together and make the actual soap. The lauric acid and other fatty acids will not mix well with the water, but at the oil-water interface, we will see the carboxylic acid groups mingling with the water since they can form hydrogen bonds. The OH, which is also called the hydroxide ion, being a strong base, really likes taking protons or H+ from other molecules. If it does get near the carboxylic acid end of lauric acid, which is right here, the OH will pull the proton off. Again, that's a hydrogen with a positive charge, and that leaves a negative charge on the lauric acid, as we can see in this demonstration. So again, we pulled off that proton, we left the negative charge, okay, and this actually forms water. So we are making water in that chemical reaction, but we're leaving behind this charged end of this acid. So this now becomes a weak base, and that negative charge there is going to be really important in the function of the soap. So now that lauric acid is called laurate instead of lauric acid because it's no longer an acid. The sodium from the original sodium hydroxide will combine with the laurate, forming solid sodium laurate soap. So the bulk of the soap that we're going to be making is going to be this laurate with sodium and a little bit of water that we're going to add, and then that tiny amount of menthol relative to the total mass of the soap. When we add more water, such as washing our hands, taking a shower, etc., some of the sodium laurate dissolves, giving us free laurate again. And what that's going to look like is now it's going to have its negative charge again, as you see here, here, and here, and the sodium will have its positive charge. In this state where the laurate is free and is expressing its negative charge, this is where it's going to be able to really do its job and function as an actual soap. When we rub this soapy water on our skin, the carbon ends of laurate, which are fat-loving or lipophilic, will surround our skin oil. The negative ends of laurate, which are water-loving or also called hydrophilic, will be surrounded by all the water from the shower or the sink, for example. So as you can see here, the non-charged or non-polar end of the laurate likes to mingle with the oils. The polar or charged end likes to mingle with the water, and that structure is critical for this soap to function correctly. So when we add more water, that'll allow the water to wash this whole, I'm going to call it a bubble right now, but then I'm going to actually reveal the technically correct term in just a few seconds. So all this water comes from the shower, for example, and it likes to mingle with these negative charges on the laurate, so that can pull that laurate out off your body into the drain, along with whatever oil is trapped in that, again, that bubble, we'll call it a bubble for now, but technically it is called a micelle. That's M-I-C-E-L-L-E. And micelles are absolutely critical in order for soap to work. So see, we washed it away, and now we're so fresh and so clean. Thank you for staying attentive up until this point. Now, from this point forward, I won't be speaking any of the narration. It'll just be text, so you can focus on the actual demonstration. I'm going to very briefly go over all the supplies with the masses that you're going to need to weigh, and then we'll get to the actual demonstration. Thank you for listening again, and I hope you enjoy the rest of this video.